Okay, so now we're going to start seeing some patterns in how these Verilog modules work. You will always have your two always blocks. Your first always block is going to be finding your next state. The next always block will be defining the sequential block. Where you determine the output depends on if it's a mealy or a Moore machine. If it's a Moore machine, then you determine the output outside of the blocks. If it's a mealy machine, you determine the output within the next state block, so within the first block. Okay, so this one we can see that our output is R, and here it is listed as a reg, which it needs to be because we are changing it within the always block, and y, little y, and big Y are current state and next state are also being changed within the always block, so they also need to be reg. Then, just like on the problem before, we set up a parameter, and we're just using that to make our lives easier, so that we're saying A is 0, 0, B is 0, 1, and C is 1, 1. By the way, going back to question 1, if after we had done that we had to do a state assigned table, then all we would do from this step is to go here and do the same table. So everything the same, except replace D with 0, 0. So everywhere you, actually, let me do it with this. Everywhere you see a D, you'd put a 0, 0. And everywhere you'd see an E, you'd put a 0, 1. And everywhere you had an F, you'd do a 1, 1. So that's what we would do if we had to do a state assigned table. But we did not have to do that. Okay, so here we're just defining A to be 0, 0, B 0, 1, and C 1, 1. And then as we look at our Verilog, we can see that we have three states, A, B, and C. And we can see that we are changing the output based on the input, because if we look at case A, it says if X, well, X is our input, and if X means if X equals 1. So if X equals 1, then it tells us what the next state is, it tells us what Y is, what the next state is, and it tells us what the output is. R is our output. So that depended on our input, so that makes this a mealy machine. So let's just start here. So we are at state A, and if X means if X equals 1, then our next state is B, and we can write this with a 1, and then I'm putting a slash, and then after the slash I'm going to put what our output is. Our output is 0. So that 1/0 means if the input is 1, follow this direction, and also the output is going to be 0. Then we get to our else. So our else means that X equaled 0. So if X equaled 0, then our next state is C. So that's a 0 slash, and our output is R equals 0 is 0. So now I'm ready to go to B. And so anytime you're doing these machines, whatever step you're on, you always want to check and make sure, do I have for every state, this is what happens if it's 1, and this is what happens if it's 0. So you just go state by state and make sure you've got all that. So for A, I've got 1 and 0. Okay, so now B. If X is 1, then our next state is C. And our output is 0. And else, that means X would be 0. Our next state is A, and our output is 1. And now we're on to C. And if we are at C and X equals 1, then our next state is C. So we go back here. and our output is 1. And if x is 0, then our next state is b, and our output is 1. And then our default, I said you always need to have a default, and especially here when we only have 3 states defined and there's 4 possible states. And here, when you see the XX, that's equivalent to a don't care. So 2'B, that means binary, 2 bits, and XX means don't care, don't care. So we're saying that if we get the other state as an input, which would be 1, 0, then the next state we don't care. It's a 2-bit we don't care, and the output is a 1-bit don't care. Okay, then this always block tells us where our reset is. So if reset n equals 0, then y is a. So this would be our reset. Else, and then this is the line you're always going to have, this line advances to the next state. So at the positive edge of the clock, it looks at what everything that was done up in the always block, and then it advances to the next state.